Now let's look at the idea of an inverse function and its graph. So we consider x squared and its inverse. So again, to get our inverse, we swap the x and the y over and then take the square root of both sides. Now we should really write, if this case, it should equate to this function y is equal to square root of x, or it could be written as y is equal to the negative square root of x. So we could write either of that way, because if we graph that one up, that would look different to what that one would be, which is the positive square root of x. Now if we graph them up, there's y is equal to x squared, and there's y squared is equal to x. So let's y squared equals x, and that's y is equal to x squared. Now, what we want to look at it here is the idea that if we graph the line y is equal to x, what do we start to notice? Okay, so if we look at it here, it's going through 0, 0, and they both go through 1, 1, and as does the line x, y is equal to x. So if you have a look at all the points on the curve here, do you notice something? And that's the question we've got to ask. What conclusions can you draw about the graphs of the inverse functions? And hopefully you're all saying, hey, the graphs reflect in the line y is equal to x, which they do. That curve, that function there, is a reflection of that relation there. So we can see that every point here gets reflected in this line y is equal to x, and that will happen with every inverse function. So every inverse function or relation, it will look like that. So is y, the inverse of y equals x squared, a function, and why or why not? So the idea is that it's not. The function, it's not a function. Hopefully you can look at it and go, hey, that can't be a function because it doesn't pass that straight line, that vertical line test. So also you could talk about in terms of there's not a one-to-one correspondence, the curve's not always increasing. So we can give a number of reasons there. So vertical line test there, okay, doesn't pass. So if we're looking at the function here, we could look at the idea of that it's not going to have an inverse function if it doesn't pass a horizontal line test. If we get that situation with our function, it can't have an inverse function. It will have an inverse relation, which y squared equals to x is, but it won't have an inverse function. So there's more than one y value for each x value, and we can look at it. An inverse function will only exist if the function is always increasing or decreasing, and we can talk about that as well. If it increases and changes, so if it does have some sort of stationary point and it does change and have a maximum or minimum turning point, it won't have an inverse function. Okay, it will have some sort of problem because we will have the curve falling and then rising, or rising and falling, and it will change and will have more than one x value for every y value, which is going to change around and become more than one y value for every x value here. So that's going to be the problem. So if the curve is always increasing or always decreasing, it will be an inverse function. So if we investigate 3x cubed and the inverse of 3x cubed, so if you're looking at 3x cubed and the inverse there, so we can see 3x cubed there, and what its inverse will look like. Well, we draw up y is equal to x and see that everything's going to be reflected. Notice where the function here, y is equal to 3x cubed, meets y is equal to x. That's where the inverse function will meet it as well. So it will touch at those points. So at those 3 points, it's going to touch y is equal to x. But then you see the reflection. All these values are reflected here in this function here. So, and you can tell as well, notice that y is equal to the function of x is, it rises, it does stop, and then rises again. So because of that, you will have an inverse function. It's not a problem. You can perform a horizontal line test on this, or the vertical line test on the inverse function, and you can tell that it's going to be a function there. So that's where we're going to be able to do this. So any of those reasons, you can give that, or you could say that it's 1-to-1 correspondence. For every x value, there's a one y value. But the nice way to say it is that because the function is always increasing, except for when x is equal to 0, where it's stationary, then its inverse will be a function as well. Now, what happens if we don't get an inverse function when we do the inverse there? Well, what we need to start to do is look at restricting our domain. And this is what we'll talk about more in when we start to do this. We need more in with some of the problems. We have to restrict our domain of our function that we start with. So something like y is equal to x squared, we either have to limit this to the situation where we'll take x just being greater than or equal to 0. If that's the case, when we take the inverse, we'll get the positive square root. Or if we take that x is less than or equal to 0, we will get the negative square root. But just taking the positive square root, that will give us a function. Because the positive square root is just that top part. It will pass the test. Or if we take the negative square root of x, then that will pass it as well. But we only do that if we start to restrict the domain of our original function, 3x, of x squared there. So if we do that, then we can start to get a function. And if we want to get a function, we have to start to restrict our domain. And we're going to be doing more questions like that, but that's the idea of how do we get an inverse function no matter what we start with. Sometimes it won't matter. Whatever we start with, we'll get an inverse function. But if we are going to only get a relation and we want an inverse function, we need to start to restrict our domain as we go along. So that's how we draw it up. That's how we start to draw it up, and how we start to get an idea of, well, how do we get a function as we go along with our inverses. And as I said, we'll do more problems and we'll see how these work out for different types of functions.